everyone. In this video, you're going to learn about what's called implicit differentiation. So up to this point, you've learned how to differentiate functions that are expressed in an explicit form. We're now going to take a look at functions written in an implicit form. Now, let's look at the difference between the two types of functions. Explicitly written functions, all that means is that the equation is solved for y. So the equation is written it's a function of y in terms of x, okay? Or like f of x is your function in terms of x. So it's y in terms of x, meaning y is equal to some function in terms of x. Well, we can also have equations written implicitly. And again, all that means is that the equation is not solved for y. So your x's, I always say your x's and your y's are going to be on the same side of the equation. So you see a couple examples here where our equations are written implicitly. Okay, again, all that means is that it's not solved for y. So technically you could, if you were given an equation written implicitly, you could just solve it for y and then find the derivative. But there are some equations where that is really hard to do, okay? So it would be easier to just find the derivative implicitly, okay? So we need to be able to find derivatives, meaning dy over dx, of equations that are in explicit and implicit form. Now, to do this, we need to really understand the meaning behind dy over dx. Okay, so let's just talk about that first. Dy over dx indicates that we are taking the derivative of y with respect to x. Now, so far, this hasn't caused any confusion because we've only taken derivatives of expressions involving x. But we need to be able to expand our differentiation techniques to include other variables, okay? Especially when we get to some real-world problems where we're going to be dealing with other variables like v for volume and t for time and things like that, okay? All right, so what do we mean by differentiating with respect to x? So if you look at example 1a, notice the d over dx, which we call the derivative operator. So when you look at this notation, this is just telling you to find the derivative of x cubed with respect to x. Well, that's easy. All we would do there is just use our power rule. The derivative of x cubed with respect to x just equals 3x squared, okay? But what if, look at b though, this one is different. Now we are being asked to find the derivative of y cubed with respect to x. All right, so in this case, you guys, you have to think of y as its own function, okay? Because remember, y equals f of x. So if y is its own function, then to find that derivative, you have to use chain rule. So think of finding the derivative of y cubed with respect to x as a composition, okay? So here's what we would do. Think of, I'm just going to rewrite this, think of it as the derivative of y to the third power, okay? Because I just want you to see the chain rule here. So if y is its own function, okay, y would be the inside function. So to find that derivative, we would find the derivative of the outside, keeping the inside the same, but then we would multiply by the derivative of the inside with respect to x. So that would be the derivative of y with respect to x, or times dy over dx. So this is just chain rule. Okay. Now, we you don't have to keep the parentheses around y. I just wanted to, you know, put the parentheses there to help you see chain rule and the outside and inside functions. But honestly, this would end up just equaling 3y squared times dy over dx. Like, that's how we would write it eventually, okay? All right, so let's look at C for a minute. This is asking us to find the derivative of x plus 3y with respect to x. Now, we can use some of our derivative properties here. If we're finding the derivative of a sum, you know, we can just make it the sum of the derivatives. So this could become the derivative of x with respect to x plus the derivative of 3y with respect to x. And derivative of x with respect to x is easy, that's just 1, okay, plus, but the derivative of 3y with respect to x, again, we'd have to use chain rule, because remember, y is it can be its own function, okay, because y equals a function. Okay, so 3 would be a constant multiple, and then we find the derivative of y, which is 1, times dy over dx. So this would end up just equaling 1 plus 3 times dy over dx. And again, you know, think of it as chain rule. So y was the inside function, okay? All right, now, what about the derivative of x times y squared? Well, first of all, I hope you're realizing we would have to use product rule for that, because we do not have a property for derivatives that says if we're multiplying two functions, we can just multiply their derivatives. Remember, that doesn't work. We have to use product rule, okay? All right, so this would end up being first times derivative of the second. Now, the derivative of y squared with respect to x would be 2y times dy over dx. Again, because we're using chain rule. Okay, plus second times derivative of the first, which is 1. So then we could just do some simplifying. Since we're multiplying here, you know, order doesn't matter, so I'd probably rewrite that as 2xy dy over dx plus y squared. Okay. So again, if you guys remember, if you're deriving y with respect to x, you're just using chain rule. And so you find the derivative, but then you have to multiply by dy over dx, because that's multiplying by the derivative of the inside, which is y. Okay. So I hope that helped explain why we multiply by dy over dx. But here are your overall guidelines for implicit differentiation. So you differentiate both sides of the equation with respect to x. So that means if you're differentiating y, you have to use chain rule and always multiply by dy over dx. Then you'll collect all terms involving dy over dx on the left side of the equation and move all the other terms to the right side of the equation. That will then allow you to factor out dy over dx on the left side and then solve for dy over dx by dividing both sides of the equation by the left-hand factor that does not contain dy over dx. Okay, now I know that was probably hard to follow, so let's look at an example so you can see it in action. Okay, so remember, when you differentiate with respect to x, if you find the derivative of y, you have to multiply by dy over dx. So, okay, here we go. The derivative of y cubed would be 3y squared, using power rule, but then times dy over dx. Okay, plus the derivative of y squared is 2y, but then times dy over dx. Okay, derivative of negative 5y is negative 5 times dy over dx. Okay, derivative of negative x squared is just negative 2x equals, and derivative of negative 4 is 0. Okay, now, all of these terms have a dy over dx, so we're going to keep them on the left side, but we're going to add the 2x to move it over to the right side, okay, because you, at this point, want to separate your terms. Any term with a dy over dx you want to keep on the left, and then move your other terms to the right. Sometimes you have to move, you know, terms from both sides, but in the end, you just want any term with a dy over dx on the left and any term without a dy over dx on the right. Okay, so now we have 3y squared dy over dx plus 2y dy over dx minus 5 dy over dx equals 2x. Okay, now I'm going to factor out a dy over dx on the left side. So that will leave me 3y squared plus 2y minus 5 equals 2x. And then to get dy dx by itself, all we have to do is divide by this big term, 3y squared plus 2y minus 5, on both sides. And then we get our final answer, dy over dx equals 2x, all divided by 3y squared plus 2y minus 5. So the derivative is also going to be written implicitly, okay? Your x and y's are going to be mixed up. All right, let's look at a few more examples. Okay, so in this example, what I really want to emphasize is if in the equation you are multiplying x times y, you have to use product rule, okay? So to start this off, you could look at this as 2 as a constant multiple times xy. So I'm going to bring the 2 down as a constant multiple, but then we're going to have to use product rule for the x times y, okay? So it would go like this. First times derivative of the second. Now, derivative of y is 1, but then times dy over dx. Okay, plus second function, which is y, times the derivative of x, which is 1. So that's my product rule. Okay, now I'm going to go to my next term. So minus 6x, okay, equals derivative of 2y is 2 times dy over dx. Okay, now I'm going to distribute my 2 to get rid of the parentheses, and then we'll start moving our terms. Okay, now I need this term to go over to the left side, and I need these 2 terms to get moved over to the right side. So remember, whenever you're doing that, you're always using the opposite or inverse operation, meaning I would have to subtract the 2y to move to the right side, add the 6x, subtract the 2 dy dx. So I would end up with 2x dy over dx minus 2 dy over dx equals negative 2y plus 6x. Okay, then we're going to factor out dy over dx. So that will leave 2x minus 2 equals negative 2y plus 6x. And then we'll just divide by the 2x minus 2 on both sides. And we will have our answer, dy over dx equals, and I'm noticing, okay, well, I'm just going to bring it all down, but I'm noticing we could do a little simplifying here. Because I'm noticing we can factor out a 2 from the numerator. And we can factor out a 2 from the denominator, and then the 2's will simplify to 1. And then, you know, sometimes you probably would maybe see that numerator written as 3x minus y over x minus 1, just so we're not leading off with a negative. Okay, let's look at another example. Okay, so what I wanted to show you is, you know, we can apply this to other problems where, you know, if you're asked to find the instantaneous rate of change, you need to find the derivative. If the equation is written implicitly, you would use implicit differentiation. We could also write the equation of the tangent line to the graph of x squared minus x cubed equals 0 at 0.11. Okay, now luckily they give us the point, so we have our x sub 1, y sub 1. Because remember, equation of the tangent line is just point slope form. So we already have our x sub 1, y sub 1. So all we really have to do is find our slope at a point, which means derivative. Okay, so let's find the derivative. This would be 2x minus 3y squared times dy over dx equals 0. Derivative of 0 is still 0. And then, you guys, all we're going to do is plug in 1 for x and 1 for y. So you could solve this for dy over dx and then plug in, but personally I find, you know, just plugging in those numbers for x and y will simplify things, you know, in Excel. So I usually like to go ahead and just plug in. And then we can just solve for dy over dx. So we would subtract the 2. So we have negative 3 dy over dx equals negative 2. And then we'll just divide by negative 3. So dy dx would end up equaling positive 2/3. And now we can just write our equation, which would end up being y minus 1 equals 2/3 times x minus 1. Okay, now the last example I want to show you involves finding a second derivative implicitly. So obviously we're going to start by finding the first derivative. So if our equation is x squared plus y squared equals 16, then the derivative would be 2x plus 2y times dy over dx equals 0. And before you find the second derivative, in this case, it is easier if you go ahead and solve for dy over dx. So I would subtract the 2x and bring it over to the right. Again, just trying to separate the variables. And then we can just divide by 2y. So dy over dx would equal negative 2x divided by 2y. And then the 2 over 2 simplifies to 1. So we end up with negative x over y. Okay, so that means to find our second derivative, we'll have to use quotient rule. So it would look like this: low d high minus high d low. Now the derivative of y is 1, but then times dy over dx. Okay, all over low squared. Okay, now, I know the directions didn't say it here, but really what we're trying to do is find the second derivative. Well, if you think about this notation here, actually the meaning is there. This is asking you to find the second derivative of y with respect to x. So what that means is we cannot leave that dy over dx there, okay? But remember, we know what dy over dx equals because we just found it. Dy over dx equals negative x over y. So anytime you're finding a second derivative implicitly, eventually you want to replace the dy over dx with what you found that to equal, okay? Previously, like don't leave it as dy over dx. All right, and then we'll just do some simplifying. So let's see, we end up with negative y. It looks like minus x squared over y. Okay, all over y squared. So let's find a common denominator. So I'm kind of focused here right now. So if I made this negative y squared over y, I would have a common denominator. And then I could just subtract the numerator, put it over the common denominator. Okay, now that's still all over y squared. But then eventually I could multiply. Remember, this is like y squared over 1. So I'm going to multiply by the reciprocal. I'm going to flip and get 1 over y squared. And then multiply straight across. And we'll have negative y squared minus x squared all over y cubed. Okay. But again, that was just a little simplifying. So, but the point I was trying to emphasize here is when you find the second derivative, you cannot leave that dy over dx in your answer, so you just use substitution because you found dy over dx, you know, before you found the second derivative. So you just substitute whatever you found previously for dy over dx, and then just simplify. All right, you guys, so that concludes the video. As always, thank you for watching, and have a good night.